we stream to 5 different streams at the same time. So I'm doing Twitch, LinkedIn, Twitter, X, YouTube, and a private Facebook group for my teachable students. So if you're a teachable student, you get an invite to our Facebook group, and that's where we, have our own little huddle, and we can talk about stuff privately. But I did a live stream last week. In fact, 2 live streams. I was supposed to do it. I was supposed to go to the airport on Wednesday, and I thought, I've got some time for a quick live stream, and so I did one and didn't quite give the result that I wanted. And then I did another one, and it just a follow on from the previous one. It also didn't give exactly the results I was looking for. I had something in my mind, and it didn't quite work. So I actually decided to step into that a bit more and look, investigate that a bit, and I know now what's going on. And the tree that we made last time was an unbalanced tree, and actually the data structure is exactly how I imagined it should be. There's no clever AVL balancing or red-black tree. It's just a very simple unbalanced tree, but the data we were putting in happened to be randomized, sort of randomized when you're putting it in. So it basically ended up not being, should we say, that unbalanced, or as unbalanced as I thought. So and this is why we got these results the last time. If you haven't checked the previous ones, have a look at them. I've got all of the source code for these streams going to be on my GitHub repository, github.com/carbot/Java specialists on Twitch. It's Twitch, of course, one of the many streams I'm doing at the same time. So, okay, so basically, let me show you what we did last time, just to revise. Very, very simple unbalanced binary tree. I didn't write this. This was done by IntelliJ's AI generator. I just basically write this, and it did it for me, which was great. It's got a very simple mod count, so that if we have if we change it whilst we're iterating, we'll get a fast fail iteration. What else do we have? Add simply adds it in the right position. Contain searches it. Remove removes it, and moves the other elements up to take their place. And as I said, I don't really know how this all works, or at least I don't really need to know how this all works, because this is all written by AI. So I'm quite happy to not have to know everything here. It's great. And then what else did we have? I made an iterator as well, although we did not implement the remove method. I just thought I'd just leave that out. It's not that important. Now, it looks like a super simple unbalanced binary tree. So and in my test, what I did was I created strings from 1 or 0 through to 999,999, and put them in. Now, what you would expect here, what I would expect, if you think about it, is if I have a tree and I've got elements which arrive ordered, then what's going to happen is, if it's not balanced, it's going to keep on putting the elements one after another until we eventually have one long list of elements as opposed to nicely balanced. However, that's not what happened, because the data that was coming in wasn't actually ordered. It looked like it, but it wasn't. And it's a very simple case. What we did is, here we generated strings, and the string was basically string 0, string 1, string 2, string 3, string 4, etc., going up to string 10, 11, 12. But of course, if we're doing sorting and it's not by numbers, then string 11 is bigger than string 1, but smaller than string 2. So it actually managed to keep it fairly well balanced because of the data we were putting in. And that's not really what I wanted to do. I confirmed that by writing a method for calculating the depth. So if I print out the depth over here, so let's go back to the tree, and let me just go back to undo that. I want to get back to the original. So this is now the what we rolled it back. Okay, that's what we started with. And what I'm going to do is I'm going to add a method over here. Let's do this. Let's say method to measure the depth of the tree, and see whether we can generate that for ourselves. Actions, let's say generate code. Actually, I want to just copy and paste that. So let's just select that and see whether it can figure that out. I had some difficulty. I tried it out this time beforehand, and I didn't quite manage to do it, to get it right. But we'll try again. Let's try generate code. Okay, let me just type it again. Measure method to measure the depth of the tree, and it did work out the method for that, but I need to just be careful. Okay, here's the depth. Basically what they do is method to measure the depth of the tree returns the depth of the tree. It's a method starting at the root, all right, and it's a recursive method with an end condition. If the node is null, we return 0. Otherwise, we do a recursive call of whatever the max is plus 1 of left and right. So this code looks quite good. I'm going to copy that and paste it underneath there. And the method's called depth. And let's call it max depth. And call them both max depth. Do refactor. So both called max depth. And then I'm going to try it out. So if you go to the tree test, after I've generated this, we're going to say print out simple tree dot depth dot max depth, and you'll see that the depth is actually not that deep. So it's 1 million elements, and it's a depth of 60. Now that is 3 times the best possible depth we could have. So it's a binary tree. So the best possible is 20. 20 is enough to contain 1 million elements, and we've got the depth of 60. Okay, because log 2 of a million is 20, just under 20. So so it's actually pretty well balanced. And what we can do to change this is we can say, let's change this to be instead. Let's change this to be formatted. So it's going to be formatted, and we're going to say 0. Let's make it 0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So let's make it 0, 10. D. So all right. So and this we can actually use over here. Use the method reference. So it's going to be string 10D formatted, and the search is going to be we're going to use the same formatted over here. Dot formatted size -1. All right. So if you run the code now the add has become linear. So when I'm adding one element, because now all the items are sorted, you've got a tree which is very lopsided. It just goes 1, 1, 1 to the next step. Hey, we even got a Stack Overflow over here because the depth is too deep. Let's change it to size of 10,000 and run it again. And now you see that the max depth is 10,000. That's what we really wanted to see before. And we also see that calling this 10 million times is just not going to run fast enough. So let's decrease that to 100,000 times instead of 10,000 times. Like there, 100,000 times, and see how fast that is. So let's run that again. And we see now with 10,000, running that 100,000 times, checking whether we contain that search, it's going to do 100,000 times 10,000 takes us 9.3 seconds to run. So that is not, I don't think that fast, right? And then the thing that we did before was we took the list. Let's change this to an array list. So if we say dot collect collectors to list, so then it's an array list. What we'll do is we shuffle that once we've written that. So shuffle, So we add them, and then we're going to say collections.shuffle of the list. And then we should see it being much, much faster. So it was 9.3 seconds, and if we run it again, let's see what we're going to get. Interesting. So it's actually not really doing any different. And that's weird. Why is it? Huh. So I'm shuffling the list. Oh, sorry. I must do this the other way around. Oh, that's interesting. Something I didn't realize before is that I'm actually saying list.forEach. Oh yeah, of course that must be below. So if I put the list.forEach after the shuffle, not before, so I can prove that this is a live stream, we end up with a simple tree of depth 32. Okay, the best possible would be like 13 or something like that, which would be enough to do, or 14 or 15 or something like that. But you can see that it's depth of 32 and the time is 16 milliseconds, right? So that's basically the result I was looking for. If you shuffle, and I tried to do the experiment earlier on, but what I didn't realize is that the input was already randomized because you're doing strings rather than and the strings were, str equals 1, str equals 2, and then 10, 15, and so on, and it actually ended up being fairly randomized anyway. The other way we could have done this is to randomize input. So for example, we do this, we say size between 0 and a billion, and again we're going to format the output so that it would be sorted normally, but because a stream is just random numbers, we should again see pretty good depth 31 over here, and the time's also really great. So the time is going to be n times log n. Well, not n times, actually n time is it's this number 100,000 times, so it's a constant times log n as opposed to a constant times n, where the n is the size. And I suspected there was something like that going on, but I wasn't really I didn't really manage to really test it very well before. If I, for example, if I increase this to 1,000 times 10,000, right? Then I would expect the time to be roughly 10 times worse. So we're expecting it now to be like half a second. Well, it might be a bit worse as it's warming up, but it should be fairly good once we've generated all those random numbers. I mean, it's 10 million random numbers now. I'm not sure if that was the best test to do. But if the values really are, so I think that was not the best example. So let's make it less. Let's make it 10 times. See how that goes. Interesting. So that's actually it's random numbers. So let's do it a different way, and let's get more consistent results. So what we're going to do is we're going to make an int stream, and we're going to shuffle it, but always in exactly the same. Oh, didn't want to do that. Always in exactly the same order. So we're going to have the same order shuffle. So what we'll do is we'll shuffle it with new random of 0. So it's always shuffled, but in the same information. So if we run that, you see its depth is 44 here. If I make it 20, 200,000, 41, and you'd expect it to be roughly one or two deeper each time you double the size, right? So I'm going to try to do 1,000 and see what happens. Hopefully this will actually run without a problem. I might have to decrease the numbers, because the problem, of course, what happens is at some point we're going to probably go bigger than the cache sizes, the level 2 cache, and then things become a lot slower. So I think I've gone beyond that. So what we can also do, which is interesting, is if you go back to 10,000, and where we saw it took about 9 seconds to run through this when it wasn't shuffled. Right, so let's take out the shuffle again and run it once more. And what we'll see is that it took about 9 seconds. If I decrease this to only 5,000, how long does it take? Well, it's probably not going to be half. It's probably going to be a quarter. No, actually, it would be half the size, half the time, because it's linear cost to do the search, right? If I decrease it again, we're going to expect that to be again half the cost. And so if you want to compare the cost of things, the more items you've got, if it's linear, like now, if it's linear, it's going to be proportionally more expensive or less expensive if you decrease the cost. Whereas if you go and make it into an order n, order log n, like if the input is randomized, then if you double the size, it's just going to have one more step because the depth is one more. I think that's quite an interesting phenomenon over here. So if you make it 10,000 and you run it, there we go. I wonder why the 10 million causes such a problem. I don't actually know. Sometimes you have weird situations. But anyway, the max depth is now written. That seems to be a fairly simple function. Unfortunately, this function is recursive, which means that if we do have a badly balanced tree, we're going to run out of stack space. So what we can try and do, this is, I think, the simplest possible answer, is to convert this to not be a recursive. So let's try and do that. And we're going to, what I'll do, just to add a test for that. Let's add a test. I'm going to do, copy this, test depth, right? And we're going to make a range from 0 to size. I'm going to make it 100,000. And it's going to be string formatted, and it won't be shuffled. So I'm going to add it to the tree, and then I'm going to say assert equals size, comma, simple tree dot depth, max depth. So that's what I would expect to see. It's going to take a bit of time to run this test, I think, but it should give us that test with the unbalanced tree. If we get a balanced tree, then we'll get a better result. Now, the problem with the current tree is that the adding is going to be fairly expensive because each time that you add, it's an order in operation. There's also here's a Stack Overflow error. It's on the test depth. Okay, so that's exactly where I wanted to see that error. Okay, so 100,000 gives an error. So if we go back to the simple tree, unbalanced binary tree, what we can do is we can say, let's change it to iterative. Let's see if we can do that. Generate new chat using selection. Change to iterative instead of recursive. And an iterative approach instead of recursive. So it uses a stack. Okay, I wouldn't use stack myself. I would use a deck, array deck rather than stack. Stack has the right name, but it's a rather old-fashioned class. It's a vector basically. Wow, so it's quite a quite a lot of extra work to do that. Use array deck instead of stack. Let's see how well it does that. So let's see, they're going to do update the max depth. Well, what I will do is I will check in the code as it is now. That'll be the binary tree unbalanced max depth method for binary tree using recursion. Okay, and so let's see what they've done. So this is the max depth. Let's copy that code. And we're going to paste that over here. And then we're also going to copy the pair. The pair was up here. The pair, which actually, we could have used a map entry for that. A private pair. Private class pair, UV. All right. Array deck must be imported, of course. Let's import that. And I'm going to actually put this, cut that out and put it over there, and then make that a var. I like using var. It does usually make things look a bit nicer. So make an array deck of the pair of node comma integer. And the pair, as I said, could be an entry. The integer would just be updated. So it's putting in new pairs, so they're not actually keeping the old pair there. So we can probably make these final, these two. Let's double check that. I think that would be correct. So final. And because we can make them final, we can convert this to a record. So we can say record pair u first comma v second, and delete the rest. So there we go. So let's make it a private record. So that's of course Java 16, I think 17 for sure. So we put first over here and second. All right. And now we should be able to count this without bombing out, without exploding with the max depth, until we run out of stack space. But I mean, like on the array deck stack space. I don't know if it's going to be correct. Of course, I hope it's going to be correct. Oh, we're still getting a stack overflow. That's weird. The test depth. Yeah, the add is also recursive. So we're going to get a problem on the add, which of course I didn't. We did have that problem before. So the thing is now we've got this nice iterative method, but we can't add. We can't create it because the add bombs out. So basically, I'll leave this in here, but I'm going to change the test to be only for 10,000, so it will actually be able to create the tree like that. There might be a way to generate the tree in a different way so that you don't run out of stack space, but I think I'm done on this one. Let's just make it 10,000 and make sure that the answer is correct. And the thing is, instead of going and changing add and remove to not be iterative, to not be recursive, to use iteration, and you can always take recursion and convert it to iterative if you want. So there's always a path to do that automatically, like we saw here. Just add a array deck for that. But the point is that instead of doing that, you want to rather change the tree so that it's balanced, and we'll do that another stream, not today, maybe tomorrow or the day after, something like that, whenever I feel like it. Yeah, if you're enjoying these streams, please leave a comment, and tell me you want more. And I was thinking about this one thing, and it's like on my bookshelf there, I've got the Art of Computer Programming, right? And I've got a friend who likes to read, and he actually printed out the Art of Computer Programming, because you can download them somewhere on the internet. And he would print out, 50 pages, and he'd read them, and then throw them away and print out another 50 pages and read them. And slowly, slowly he got through the entire 4 volumes of The Art of Computer Programming, which turned out to be extremely useful for him, because he could, he'd be looking at something and wait a moment, I remember seeing an algorithm that actually did exactly this. In my project Euler, I've often went and looked up in Art of Computer Programming for some hints on that. Now this friend of mine is really bright. I mean, he's got a great memory and he can remember stuff like that, algorithms and little facts and so on. My memory is not that good, but ChatGPT has obviously read The Art of Computer Programming and knows all the algorithms in there. So we can really have some fun with that, and I want to start exploring some algorithms as well, doing different types of searching and different types of trees, etc. It's really great having a friend like ChatGPT who we can just ask anything, and they sort of know sort of everything. Not everything 100% correct, but well enough to get us on the right track. So this is very exciting. I hope you are using generative AI where you can, and playing around with it, because it is not the future. It's the present. And if we don't use it, we're going to be left behind, because others will use it and they'll just leave us behind. So I hope you're enjoying them, and please leave a comment. And that's it from me. Until next time.